In the previous lecture, we studied the principle of the negative feedback systems. For practical circuit design, we usually need to measure or derive the transfer function of a closed loop system. So in today's lecture, we are going to introduce a classic theorem, which we call as the feedback theorem, to derive the transfer function of a closed loop system. So first, let's talk about the definition for this feedback theorem. So basically, it means that we apply the technique of double null injection By doing this, we can use the null double injection to derive the important transfer functions. Of a closed loop feedback circuit. So we can use a block diagram to show you what are those injections and what are those coefficients of the transfer function. So first, let's plot a regular negative feedback system. So we have a calculator to calculate the reference. So here is the reference input. We denote as UI. And here is the feedback signal. And this is the error. The error is the difference between the input reference and the sensed output signal. And we have an error amplifier. So this is the error. And the output of the error amplifier goes to the main plant of the system, right? And here is the output. We denote as UOS. The feedback is that we sense the output signal using a sensor block and goes to the calculator. So this is the regular system, right? So here we have the terminology as null double injection. Means that we cut the loop. For instance, we cut loop here, and we inject a signal. So injection. And we define this as UZ, right? UZ in S domain. Then we would have the input of the calculator here. We denote as minus UYS. Means that the signal goes over this loop, gets amplified, and become minus UY here. And this calculator output we denote as UX. So here are the signs of the calculator as plus. And meanwhile, we can mark the loop gain, right? Loop gain is we go over this loop. The loop gain is denoted as TS. So here, uz is the injection source. It is the tool which help us to derive those important transfer functions of the closed loop feedback system. So the basic rules here are: first, we inject uz, right? After a source, uy. The uy is here, right? Which is proportional to the error signal. So that is the first rule, right? And the second rule is that the forward portion of the feedback loop of the feedback loop must contain no parallel pulses, right? That allow the amplified signal to reach the output. Without passing through the injection point. So this means that the injection point will be a masked pulse of the signal from the input to output, right? So we must, so the error to the output, this pulse must contain must include injection point. So as this diagram indicates, right? So this point is a masked pulse for the signal through the error to the output. So that is the two conditions to apply the feedback theorem to calculate the transfer functions of a closed loop feedback circuit. So based on such a diagram with now double injection, we can calculate the overall transfer function. So the overall transfer function is denoted as GS then GS will be equal to the output signal divided by the input signal. So this will be equal to the summation of two parts. First part is G infinity times loop gain over 1 plus loop gain. Second part is G0 times 1 over 1 plus T. So here is the conclusion we made. Later on, we are going to prove this argument. And also there are two coefficients. One is G infinity and G0. We are going to define it and derive it in the next page of the blackboard. Okay, now let's erase the blackboard. Okay, we have erased the blackboard, and also I have moved the transfer function equation to the top left-hand side. So in this page, we are going to discuss about what is the null double injection phenomena and how can we define those coefficients of the closed loop transfer function. So we can see that in this formula, the first key parameter is the T, right? So T is the loop gain. As I marked in the diagram of the system here, the loop gain. So basically Ts can be expressed in the formula that the ratio between the Uy divided by Ux, right? So this Us goes through the loop and reaches Uy. So if we divide Uy by Us, this will be the loop gain, Ux. But there is a condition that when we measure or calculate the loop gain, we would assume that we only have the injection input. And this overall system input we consider is 0. But pay attention that for this calculation, the injection still exists. And the second parameter in this closed loop transfer function is the G infinity, right? So we call this as the ideal forward gain. G infinity. Similarly, we also have a formula to define this parameter, so which is the ratio of the output signal and the input signal. Under the condition that the Ny, Uy is nulled to 0. So this word null means that we try to tune the UZ to try different value of UZ to ensure that after through this input and feedback, the Uy is tuned to 0. Okay, so that is the word null means. Means Uy is not to 0. And Ui exists. So for this calculation, Ui is not 0, right? We change Uz to ensure that Uy is tuned to 0. All right, So the next parameter in this formula is G0, right? G0s. So G0s, we call it the direct forward transmission. Gain through the feedback pulse. So similarly, we can also write a formula to express G0 mathematically. So G0 will be equal to the ratio between the output and input, similar to G infinity, right? But different conditions. For this time, we know Ux to be 0. Okay. So Ux not to 0 by tuning the Uz to compensate this minus Uy, ensure that Ux is fully cancelled to be 0. And Ui still exists. So what's the physical meaning for this condition? So this condition means that if we know Ux to be 0, so this means that the feedback loop does not control the output. Right, this is pretty straightforward, right? Because here becomes 0, right? It makes sense that the feedback loop does not control the output. Okay, and besides those 3 parameters which are listed here, we still have the 4th parameter. We call it the null loop gain. So we usually use Tn. The letter n represents null to indicate this is null loop gain, right? So we also have a formula to define the null loop gain. So which equals to the ratio between Uy and Ux, right? Uy and Ux. Given the condition that the UO is not to 0. It's like we try to tune the Uz to compensate the system to ensure that the output signal U0 equals to 0, right? Then we call the ratio between Uy and Ux as the null loop gain, right? Null loop gain. So this UO null to 0 means that we still have Ui. The input exists, non-zero. And meanwhile, the UO is not to 0. So based on the 4 parameters we have just listed, right? So we indeed has a reciprocity relationship. So which gave us the relationship among those 4 parameters. Basically, it's like the null loop gain divided by the loop gain, Ts, equals to the ideal forward gain divided by direct forward transformation gain. So this relationship means that as long as we know the 3 parameters, we can find out the 4th one based on the reciprocity relationship. Okay. So in this subsection, we have introduced the feedback theorem. So by injecting the testing signal, we can define the coefficients of the system transfer function. So next, we are going to derive this theorem and try to apply this theorem in the power electronic converter analysis.